Good morning, everybody.
Good morning,
Good
ma'am.
morning, Miss.
Morning, ma'am.
Okay. Today, till last class, we were studying about the discovery of the subatomic particles like electrons, protons, neutrons. And no, neutrons were discovered very lately after 1932, and also electrons and protons was discovered. Till date, it was considered that atoms was indivisible. So later on, when the electrons and protons were discovered, there came the need of atom models. How are these electrons and protons are distributed inside the atom? That was discussed by the atom models. And the first atom model was put forward by Thomson, and we have already discussed about the Thomson's model of atom, that Thomson's plug pudding of model of atom, where electrons and the protons were equally distributed. We have discussed about it. Now, since we have could find many limitations for Thomson's model, the next model put forward was by Rutherford's atom model. Okay, Rutherford's nuclear model of atom, or Rutherford's alpha scattering experiment. Okay, the three scientists, Ernest Marsden, Rutherford, and they put forward this theory, put forward this atom model, and the major contribution was done by Rutherford, and hence it is known as the Rutherford atom model. And I'll explain to you first the Rutherford's alpha scattering experiment. Okay, now. Okay, this is the Rutherford scattering experiment. We'll see that.
Rutherford's scattering experiment. Thomson's atomic model is the simplest model of an atom showing the arrangement.
See, this is the Thomson's atom model, which we have studied. See here, the electrons and protons are equally distributed in the atom, so that it is same everywhere. It is having a similar behavior everywhere for the Thomson's model. Now let's see what are the observations and how the experiments are done by Rutherford.
Of electrons and protons. In this model, the positive charge of an atom is evenly distributed in a sphere and the negative electrons are embedded in it. It is also called the plum pudding model. In the year 1911, Ernest Rutherford, along with Hans Geiger and Ernest Marsden, conducted a series of experiments with the aim of exploring the structure of an atom. These experiments were called Rutherford's scattering experiments.
Okay, so these three scientists, they did a lot of experiments, and collectively this is the Rutherford's experiment. Okay.
The experimental
See, this is the experimental setup done by Rutherford. Rutherford experimental setup consists of a radium source, that is an alpha source. Alpha source means that is alpha particles, which are the positively charged particles. And this alpha source, this is kept in a lead block. This lead block is provided with a narrow slit, so through this narrow slit, the alpha radiations are able to come out of it, and this alpha radiation is allowed to fall on a thin gold foil. See, this is the thin gold foil. This gold foil is having a thickness of around 100 nanometers, very thin. And when the alpha particles are falling on this gold foil is kept in a zinc sulfide screen. Now, what is this importance of zinc sulfide screen is that when the radiations fall on it, it's whatever is happening to that radiation, what is the path of that radiation, whether it is moving straight, whether it is having deflected, whether it is reflected by what angle they are reflecting, all those things you can identify when this alpha radiation fall on the gold foil and it is traced by the zinc sulfide screen. Okay, so when the alpha radiation fall on the zinc sulfide screen, that particular point scintillations will be observed, and based on that they predict what is happening to the what has happened to the alpha radiations. Let's see that one by one.
Setup consisted of a piece of radium, which is a radioactive metal, placed in a lead block. The lead block had a slit to allow only a narrow beam of alpha particles emitted by the radioactive radium to pass through. The alpha particles escaping from the narrow slit were directed to a thin gold foil of a thickness of approximately 100 nanometers. A movable circular screen coated with zinc sulfide was placed around the gold foil. The alpha particles produced by the radium escaped through the slit, struck the gold foil and got scattered. The scattered alpha particles were detected by the zinc sulfide screen in the form of light flashes or scintillations. Different portions of the screen were then examined to determine the deflection pattern of the alpha particles. It was observed that
Okay, so this is it. So this alpha particles was allowed to fall on the zinc sulfide screen, and these radiations they were scattered, and how they were scattered was identified by using zinc sulfide screen. Now, see, what is the first observation? There are mainly three observations that was made by Rutherford. The first observation was made that most of the alpha particle, it remained undeflected. It passed through the gold foil without any deflection. Okay, so what is that? The first observation that mainly there are three observations. The first observation was that most of the alpha particle it passed through the gold foil without any deflection. Okay, so however it is coming and it is hitting this gold foil, it is being moving in the same direction. There is no change. Now, what is the second observation? The second observation was made that, see, a few particles, when they are passing through the gold foil, they were deflected by small angles. Most of the radiation they pass through the gold foil without any deviation. A few particles they're deflected by small angles. A few particles were deflected by small angles. And what about the third observation? The third observation was that a very few alpha particles, a very few alpha, that is like 1 in a 20,000, like 1 in 20,000, that radiations they were reflected back by 180 degree. There are three major observations done by Rutherford. The first one is that most of the alpha particle it passed through the gold foil without any deviation. The second one is that a very few alpha particles they pass through the gold foil, deflecting through small angles. And the third one is that a very few alpha particles, like 1 in 20,000, they were deflected back in 180 degree. Okay, okay. See this?
most of the alpha particles remained undeflected and passed through the foil. A few alpha particles got deflected through small angles, and hardly any alpha particles got deflected through large angles or came back with a deflection of 180 degrees.
So understood, these are the three main observations. Can anyone tell me what are the observations? What is the first observation?
Most of the particles,
Yeah, continue. Continue, children.
Most of the alpha particles pass through the gold foil undeflected.
Yeah, that is very good. That was the first observation. What is the second observation? What is
Some alpha particles deflected by small angles.
A few alpha particles got deflected by few angles. Good. What is the third observation?
A very few alpha particles
Uh,
bounce back, that is, were deflected by nearly 180
yeah, they were bounced back, they were deflected by 180 degree. So now based on three observation, Rutherford, they tried to propose new model of atom. Say, these three observations proved that Thomson's atom model is not the right model, because if Thomson's atom model was the right one, if you should not get three observation, we'll get only one observation, because entire atom is the similar everywhere. Everywhere it is having the equal number of protons and the electrons, so there is no difference in how the atom is arranged. So these three observations proved that Thomson's atom model is not the real one, which we can rely upon. So then they could try to put forward the new model for the alpha scattering experiment, and that is the Rutherford atom model. So based, what is the first observation? Most of the alpha particle pass through the gold foil undeflected. And what does that indicate? It indicate that most of the space of the atom is empty. Most of the space of the atom is empty. That is what is the indicated. Now what is the second observation? What is the second observation? A very few alpha particle got deflected through small angles. When does the you know that alpha particles are a positively charged species. Alpha particles are a positively charged species. When does a positively charged species deflect? When does a positively charged species deflect? When it comes in contact near a positive charge or a negative charge. When does it get reflected? When it coming to near a positive charge or a negative charge?
Near a positive charge.
When it comes in, very good, when it comes near a positive charge, it is getting deflected. So it is coming in contact with some positive charge. Yeah. Then what is the third observation? A very few alpha particle got deflected through 180 degree. When does something deflect back in 180 degree? When does something which is reflect back in 180 degree? Okay, when does something reflect back through 180 degree? Chips. Okay, suppose you are throwing a cricket ball. Okay, you are taking a cricket ball, you are throwing it onto the wall. It reflects back here, right? When does it reflect back? When does it reflect back?
When it hits a massive object.
Yeah, when it hits, very good. When it hits a massive object, it is deflecting back. So, a very few alpha particles, they deflected back means they might have hit something which is very massive. They might have hit something which is very massive. Look at here.
These observations did not hold true to Thomson's atomic model, where it was expected that the positively charged alpha particles would pass through the weak electric field largely undeflected or slightly deflected. Thomson's atomic model was discarded since it failed to explain Rutherford's observations.
Okay. Thomson's atom model was rejected because it couldn't explain why he got the three different observations. Okay.
Based on the observations, Rutherford concluded that there must be a large empty space within the atom, since most of the alpha particles passed through the gold foil without any deflection.
Yeah, see here, most of the alpha particles, they are passing through the atom undeflected. Maybe it is because most of the space of the atom is empty. Most of the space of the atom is empty. See, you are getting this observation by looking at the zinc sulfide screen. How the scintillations occurred on the zinc sulfide screen. He had made the observation, and the first observation is most of the alpha particles passed through the gold foil without any deviation, which indicates that most of the space of the atom is empty. Most of the space of the atom is empty. Understood? Okay? Okay? The next observation.
Some alpha particles are deflected to certain angles, which means there is a heavy, positively charged mass present in the atom.
See here, a very few alpha particles are getting deflected. Why do they get deflected? They're getting deflected because they are coming near something which is positively charged. Okay, there is a heavily positively charged mass concentrated at the center of the atom. When these alpha particles are coming near this positively charged species, they are getting deflected. They're getting deflected. So what is the next one? So first observation, most of the atom of the space of the atom is empty. These alpha particles are getting deflected because they are coming in contact near a certain positively charged particles. Okay, that is the second observation and the conclusion made from it. Now, what is the third observation and the corresponding conclusion?
This positive mass must be concentrated in a very small space within the atom, since only a few alpha particles showed large deflections.
Yeah, see, only very few particles have deflected back by 180 degrees. They were reflected back in 180 degrees. Now, before that, massive part, that is the positively charged space, it will be covering only a very small space of the atom, right? Why? Because only small atoms are only a very small fraction of the atoms were getting deflected. If the positive part is very huge in size, then what happened? Most of the radiations might have got deflected. But here only a very few radiations are getting deflected. That is why, because this massive part, the positive part is encountering or covering a very small space of the atom, right? And next.
The bouncing back of very few alpha particles with a deflection of 180 degrees indicated a direct collision with the positively charged mass of the atom.
See? They're deflecting back by 180 degree. If they are deflecting back by 180 degree, that occurs because there is a direct collision between this alpha particle and that massively positively charged species. Okay, now there is a direct reflection back that happens only if it is coming in direct hitting contact with something which is massive. Okay, which is very massive. Understood? So that what are the three conclusions? The most of the space is empty, and he concluded that most of the radiations are getting not moving without any deflection, indicates that most of the space of the atom is empty, and a very few particles, they come deflected through small angles because they are coming in contact with something which is positively charged, and because this positive charge and positive charge is getting deflected, they are being deflected, and that space, that positive charge covers only a very small space. That is why only a few particles are getting deflected. Now, certain particles are reflected back by 180 degree. Why do they reflect back in 180 degree? That is just because that they are reflecting back in 180 degree. It is because that is hitting very something which is very massive. That massive part, it covers only a very small space there. It covers only a very small space there. Why is it covering a very small space? How do you understand that it covers a very small space? It is because why it is because only a very few particles are getting deflected. Okay, and Rutherford, he named this small, massive part which is positively charged as nucleus. And till today, the concept of nucleus is holding good. And that is the importance of Rutherford model. Till today, the concept of nucleus is holding good, and it is also otherwise also known as Rutherford's nuclear model of atom.
Later, Rutherford termed this positively charged mass as the nucleus and proposed it to be located at the center of the atom.
Understood? Understood?
Let's quickly summarize the observations and conclusions of Rutherford's scattering experiment.
Okay, who can tell me what are the observations and conclusions made by Rutherford?
Yes, ma'am.
Okay.
According to first observation, that is most of the alpha particle passed through the straight line through the gold foil. It came to the conclusion that most of the space of the atom is empty.
Very good. Okay.
And according to second observation, that is a small number of alpha particle were deflected by large angles. It came
Through
to a
small
conclusion that
angles. Okay.
it came to a conclusion that it might have come in contact with some similar charges.
Yeah, right.
And according to third observation, that is a very small number of alpha particles, they reflected back by 180 degree.
Good.
Its conclusion is a small massive positive charge, that is it
And
might
that
have come in contact with some
something which is
massive.
very massive, and that massive part which you call it as a nuclear model nucleus. And later on, based on this, Rutherford said that the first Rutherford model of atom consists of nucleus at the center where the entire mass of the atom is concentrated and the electrons are revolving around this nucleus. So this is the Rutherford model of atom. Hope you have understood this, right? Hope you have understood this. Okay, children? Thank you.
Yes, miss.